Good morning in Mexico. Good afternoon here in the United Kingdom. My name is Antonio del Rio, and I am director of the Center for Mexican Studies UNAM UK. It's a great pleasure to welcome you all here in this session on our seminar series. This series provides a space to share research, foster dialogue, and strengthen academic collaboration between Mexico and the United Kingdom and beyond. Today is my great pleasure to introduce Dr. Ugo Patrick Okoye, a professor in the Instituto de Energías Renovables at UNAM. And let me say some words about Okoye here. Dr. Okoye obtained his bachelor, master, and doctoral degrees in chemical engineering all in Namidi, Nigeria University and University of Newcastle upon Tyne here in United Kingdom and University Saint Malaysia in Malaysia. The last one was his doctoral degree. He carried out postdoctoral research in Shenyang University of Technology in China, and right now he is a professor in National Autonomous University of Mexico. His research integrates clean energy and material science with a primary focus on waste valorization for sustainable fuels, catalysis, energy storage, material and environmental remediation technologies. He has published more than 100 peer-reviewed articles with more than 4,000 citations, and he has supervised both undergraduate and postgraduate students. Dr. Okoye, thank you very much for being here, and it's a pleasure to having you. But before I gave you the floor, please, everybody that is accompanying us, please, can you make questions using the chat box here in the Zoom session or in YouTube? The presentation will last around 45 minutes, followed by some times for question and discussion. And please, if you are following in YouTube, share the link to your friends. Dr. Okoye, thank you again for being with us, and the floor is yours.
Thank you very much, Dr. Derio, for having me. I am very happy to be here, and I am going to present to you, everyone here, depending on where you are. Good morning, good afternoon, and good night for some people who are sleeping already. The world is a very small and global place. Today we are going to be talking about porous carbon, a versatile platform for energy, environment, and catalysis. And this talk is purely based on selected past works on carbon derived from biomass and the liquid glycerol. So let's delve into it immediately and then do some good presentation. So in our content, we're going to be talking about some motivation about our work, biomass resources, conversion and applications, porous carbon, production and activation. And then we are going to highlight more on some case studies about aqueous phase adsorption, case studies about energy storage, which includes supercapacitor and hydrogen, and then some case studies on catalysis, which is actually get towards valorization of glycerol. So what is our motivation? The black gold, like I used to call it, is a material that is very fascinating. It is very interesting material because of its physical-chemical characteristics. This material, which is carbon, when I mean carbon, we have to differentiate between the charcoal that we have, We have to also differentiate within the coal that is mined as a mineral, and then we have to differentiate in these several forms of it. In fact, we know carbon, which is an element in the periodic table, has several allotropes. Also, it has several hybridization. But today we are going to talk about porous carbon, which we are thinking about mainly activated carbon and biochar. The beauty in this material is that it has very high surface area and the pores can be adjusted. It also has good electrical conductivity and chemical stability and has diverse applications. And one of the most interesting things is that whereas some chemicals are synthesized in the lab, in the plants, or dug up from the ground or mined from the ground like the minerals, this material can be produced from low-cost, widely available, often waste-derived sources. Hence, it is economically practicable and environmentally sustainable. So, there are several types of biomass resources that we know, but these are just selected, which could be grouped. There are monton, there is a lot of it. For instance, we have the municipal waste, organic fraction of our municipal waste, forest residues, agricultural residues, animal waste, and even some energy grass, which currently it is the main reaction focus of all researchers. So for conversion technology of biomass, we have several types of conversion, and it can be broadly categorized into two: biological conversion and thermochemical conversion. This biological conversion includes some anaerobic digestion, photolysis, and thermochemical conversion is far broader than that biological conversion. In thermochemical conversion, we have combustion, pyrolysis, hydrothermal processes, gasification, carbonization. So the term thermochemical conversion means that it is a thermal treatment combined with a chemical reaction that is happening. And eventually, when these technologies are applied, we obtain some products of gaseous fuel, depending on the conversion process, liquid fuel, solid fuel, and even chemicals, that is, fine chemicals from it. The applications of these products are very vast. The fuels are biofuels. Then chemicals can be applied in cosmetics, in polymer industry, in all sorts of chemical industry. And even in the environment, for instance, the porous carbon obtained from this as a solid material can be applied for water treatment, for soil agents, for crop stimulants, and so on and so forth, especially biochar that has fund application in soil remediation. So when we are talking about biochar and activated carbon, we want to make some distinction between these two materials. This distinction is based on the features such as the production, surface area, how stable it is, application, cost, and equally what they do in the environment. So in the production, of course, we use mainly pyrolysis for biochar under limited oxygen and at a lower temperature. But for activated carbon, because we need a carbon-rich material, we usually use some higher temperature, and in fact, the production could go towards physical or chemical activation. And in a bit, I'm going to talk about the difference between physical and chemical activation. Then the surface area of biochar is considerably lower compared to that of activated carbon, because in activated carbon, it has well-developed micropores. And these micropores and even the pore volume translate to the surface area. If you apply some model, which we are not going to talk about today because of how extensive that is, you will see that you can calculate the surface area. And obviously from biochar, because it is obtained at a lower temperature and there is no activation at all, it does have less developed pore structure and lower surface area. In terms of stability, biochar, of course, is long applied in soil and it is used for long-term carbon sequestration. But then uh, activated carbon is, of course, stable under operational conditions, but not used for carbon sequestration. In fact, it is used in the industry where water purification is being done, gas adsorption, or CO2 capture. And in terms of its environmental role, of course, the biochar is mainly applied for climate mitigation and soil health, whereas the activated carbon is specifically engineered for industry. If we are going towards this talk, you will begin to see some of the different ways that we applied biochar and activated carbon in processes for instance, aqueous phase adsorption or for catalysis when we used biochar. So, like I said, there are several types of activation. We could have the physical activation or chemical activation. The difference in this is that chemical activation requires a chemical agent to happen, whereas the physical activation do not require a chemical agent. In essence, physical activation is a two-step process where we do carbonization. The term carbonization is temperature treatment, controlled temperature treatment at some elevated temperature between 600 to 800 degrees Celsius, and then activation in some oxidizing atmosphere. So for physical activation, you have some oxidizing gases like CO2 or steam. One of the challenges with physical activation is that is either you are using CO2, you have narrow pores, or you are using steam, you have much wider pores. And then the problem is that some of these agents or the oxidizing agent used in physical activation for this process makes it very difficult to control the porosity. And if you cannot control the porosity very well, then it becomes even challenging to have an application because depending on the type of application, the surface area is very important as well as the porosity. And if you use steam to do an activation, there are higher chances that you lose some of these um, functional groups that may contribute in one way or the other to enhancing your process. For instance, literature have shown that if you use nitrogen in your activated carbon, if nitrogen is accumulated in your activated carbon, the chances of higher storage of the hydrogen or chances of higher storage of some gases is much higher compared to when you don't have nitrogen, which is a heteroatom in the surface of activated carbon. So with chemical activated carbon, the catch in this scenario is that these molecules or the chemical agents, as they are decomposing, they leave a fingerprint that is somehow related to their molecular radii. So they can equally etch the surface of the activated carbon if overused, and this also can cause pore collapse. So in all the situation, you have to optimize the process for you to know the optimal conditions, the optimal chemical agent that you will be used. But one of the challenges is that if after production, the chemical activation, you have to wash several times to ensure that excess of this salts or acid or the chemical agents used is actually removed from the activated carbon. This is because activated carbon in itself for use has a regulation. So it does have the number of foreign elements, whether alkaline, heavy metals, that should be there before it can be used. Otherwise, we are going to be causing pollution downstream. So the challenge there is that during this washing, some pollution is generated. That is why if you use, there are several chemical agents like sodium hydroxide, zinc chloride, potassium hydroxide, sulfuric acid, phosphoric acid. Once you are using these chemical agents, be careful, because when you use them and try to wash it off from the material after production, of course, some of them will decompose, but there are excess in it. If you try to wash it off, you may generate more pollution. Hence, it is always ideal to use those chemical agents that are far more environmentally friendly, like potassium carbonate. So we have different physical forms of activated carbon. We have the monolith or the honeycomb activated carbon. It could be granular activated carbon, pellets, powdered activated carbon. Depending on the application, you can adopt any of these. For instance, some people have used monolith activated carbon for impregnation of metal oxides for catalysis. Some have used this also in distillation columns or separation columns to be able to separate some material from the other. Some have used this in adsorption column as well. So your application will determine the forms of activated carbon that you use. Now we are going to talk more about some case studies that we have done. One of these case studies, very fascinating, is aqueous phase adsorption. And what is aqueous phase adsorption? Aqueous phase adsorption refers to the process where contaminants, when we mean contaminants, it could be dyes, it could be heavy metals, and so on and so forth, are, which are dissolved in water, are removed or attracted and held onto a solid surface that is such as activated carbon. So this aqueous phase adsorption is, of course, with carbon, is a tertiary wastewater treatment process following secondary biological treatment. And it is used to separate pollutants such as dye, heavy metal, organic compounds that microbial treatment cannot remove. So we have several forms of it, but the real deal is in the natural environment, we have water that is polluted with several kinds of pollutant. Many a times, activated carbon are tailored to do one pollutant. And the vast amount of literatures, about 67,000 of it, reported only one pollutant for one material. So the real catch is we need to try to do binary, ternary, or even stage column adsorption. And these are some of the recent studies that people are conducting at the moment. So for our case, we looked at a biomass resource called macadamia nut shell. Macadamia nut shell is just a nut that is quite abundant in Australia, but also here we have a lot of macadamia nut shell. For instance, Mexico produces about 35,000 tons of this macadamia nut shell every year. And the cities in Mexico that produce this is Puebla. We have Chiapas, which is the main place where it is produced, and also some places in Veracruz. In fact, this macadamia nut shell is what many farmers here in Mexico resort to because of some challenges they are having with the tree, the cocoa tree, where they use for cocoa, or the coffee tree where they use for coffee. So when the disease is struck, this macadamia thrives and it can produce a lot. So we try to use macadamia, not shells, and then transform it into activated carbon for binary pollutants. These pollutants are model pollutants like antibiotics and methylene blue. Why are we focusing on methylene blue? If you have swimming pool in your place, the blue color of that swimming pool is methylene blue. It is also used widely in textile, in coloring, in so many places. And antibiotics, especially amoxicillin, is the daily antibiotics. In fact, our body system do not absorb all these antibiotics. A lot of them is excreted from our system, and people who abuse antibiotics even create further problem. The challenge with antibiotics spill is that it is an emerging pollutant. There is no general consensus on the limit of this material in the water body, in the system, and so on and so forth. So it has become a real problem that needs to be solved. So we chose these two model pollutants for removal using our macadamia nut shell. This article, published by my master's student, in talks about a cationic and an amphoteric material. So for us to produce activated carbon, we optimize the process. We use K2CO3 potassium carbonate, which is a far more environmentally friendly material compared to zinc chloride. And under optimal conditions of 900 degrees Celsius, 2:1 potassium carbonate biomass and 1 hour, we obtained a superior material that were able to give us a maximum absorption capacity of 578.9 milligram per gram. This absorption capacity is a combined absorption capacity of the combined pollutant, because we combine these two pollutants in one system and we try to remove the two of them. So we characterize that material. You could see that there is some imprints here. This channel and in this part, it is obviously looking as if there is no pores in it. But then we have pores here and there. And this is an SEM micrograph, scanning electron microscopy we used to obtain this image. And you could see that our material indeed is porous. And we have a surface area of 1,225 meters square per gram. In perspective, a standard football field is between 4,000 to 8,000 square meter. So in essence, if you have about 10 grams of this material, you have a complete surface area of a standard football field. That is an analogy of the type of material that we produced. And when we looked at the isotherm, we found out that this isotherm, according to IUPAC, that is International Union of Pure and Applied Chemistry, you find out that we have a combined 2 and 4. 2 in the lower region of the relative pressure and 4 in the upper part, with some space between the adsorption and desorption. This space is due to capillary condensation, and it is type 4 hysteresis, they call it. And the distribution of our pores, we found that we have a pore that is very close, from about 1 point something to about 8 nanometer. This will tell you that we have considerable micropore and equally mesopore in it, because in this part we have, in fact, to give you a glimpse, we have different types of pore. We have micropore, which is about less than 2 nanometer. We have mesopore from 2 to 50 nanometer, and then we have macropores from 50 and above. Usually for liquid adsorption, gas adsorption, and even energy storage, it is preferable to have either hierarchical pores of micro-mesopores or micropores. So the results of our adsorption shows that between 2 to 12, we have constant amoxicillin, constant methylene blue removal. But usually, methylene blue is a cationic dye, so it has some positive ion. If we have a pH in the acid sites, we also have more positive ions, so they repel each other. And from here, we have that our surface is about 4.5. Usually, it is not supposed to have full removal of methylene blue, but this is an interesting knowledge in research. In fact, it is one of our stellar findings in this work. And what is the cause of this? Why are we having an unexpected behavior for this removal? It is because there is some interaction of these two pollutants to show you that pollutants in the water, they interact with each other. And many a times when the pH is elevated or reduced, there is some modification of even the adsorbent that you want to use. And hence, there is a non-electrostatic interactions like van der Waal or hydrogen forces. But then in amoxicillin, we also have a very strange concept. But then we have near neutral pH. Our amoxicillin gives us our best result. And this is in part because this amoxicillin is, they call it amphoteric. So it does have positive and negative part, that is acid or basic part, depending on the pH. So in the solution, where it is near neutral pH, they call it zwitterionic ion or zwitterionic effect, which helps to reduce repulsion from negative surface. Also, we can have forces like pi-pi interactions and hydrophobic interactions of the carbon, which may dominate electrostatic interaction. And this is quite new in this field. And we have actually laid these things down and try to explain why these things happen in this way. Another aspect is the cross-linked chitosan agave leaves. Here in Mexico, we produce tequila, and we take tequila, although not many people drink alcohol. But then tequila is a dairy drink that is produced here, and some cities like Veracruz, Jalisco, they produce a lot of tequila with a lot of the leaves. The leaves are dumped or either used for fiber or naturally landfilled. So we try to combine this leaf with chitosan. Chitosan is a byproduct or a product from the back of the crustaceans or the shrimps, the prawns, and so on and so forth. So when it is deacetylated, then you have to perform some other processes and you'd have some chitosan. So we combine this chitosan by dissolving it in 5% acetic acid and then mixing it with carbon of different ratios. And then we try to use a syringe to bead to form these small beads of chitosan in 1 molar sodium hydroxide. And then we obtain this form of the material. We then try to cross-link this material because the challenge is after this, it is physically combined. The cross-linking stabilizes it against chemicals. For instance, if you are doing effect of pH and you are under acidic conditions, if you do not cross-link this material, it will thoroughly dissolve. So, and then after cross-linking, we freeze dry to obtain these pellets that you see. Our results were also very fascinating because we have very rich porous materials that were able to remove up to about 79% of arsenic. And what we used was arsenic 5. And from here, you could see that the isotherm is way different from what we had from the last one. The isotherm here is way different from that. This isotherm do not have a space in between. So there is no hysteresis that is happening. This isotherm is also another type of isotherm. They call type 1 isotherm, with pores even far more narrower in the micropore region. But then something fascinating happened. If you put chitosan in this carbon, here is our carbon, and then here is carbon with the chitosan composites, and here is carbon with the chitosan composite plus adsorbed arsenic. Here you could evidently see that in this part, which is the amount of nitrogen adsorbed, it has lower here and even far lower in this part. This shows that putting chitosan in this carbon actually disrupt the surface area, blocked some of the pores that we have, and eventually we have lower pores. Okay, so why is not moving? Okay, so the textural characteristics of this material shows that we have over 2,055 square meter per gram. This shows obviously that our material, if you use about 5 grams of it, you will be having about standard football field. And then the best material, which is 80% of chitosan and 20% of activated carbon, the surface area is even far lower and then even worse when the arsenic was put. Eventually, you could see that we have carbon-rich material with the activated carbon, but adding the chitosan introduced the nitrogen group, some form of chlorine, and more of oxygen. And hence, we have lower carbon in this. But why we did this is to ensure that arsenic is removed. And in a bit, I'm going to explain to you the challenge that we had. When we used only carbon to do that, we find out that from our point of zero charge, which is equally near 6.5, we were not able to remove a lot of arsenic because arsenic in water also has negative ions. So they protonate and form some arsenate ions or arsenite ions. So we tried our best to see if we can have a positive surface, high rich positive surface, to be able to remove the negative surface. Remember, like charges will repel and unlike ones will attract. So the point of zero charge, which is the point at which the pH of the surface of an adsorbent carries electrical or no net electrical charge or electrically neutral, is 6.5. And in this point of zero charge that we have here, we can break it down into two. At the back, which is from 6.5 to 2, and from 6.5 upward. Okay? When we have less, when the pH is far less than the point of zero charge, the material surface is positive. So we have some protonated amine group in the chitosan. Remember, we have a lot of nitrogen. So this nitrogen infers an amine group. And this vice versa happens when, of course, we go from 6.5 to 12. So in solution, arsenic group exists in forms of anion, which is negatives, at the pH level below 6.5. So it is now easier to take it because our surface is positive. But then if we go a pH above that, then it has deep protonation of the protons, and then they have competitive adsorption, which reduces the adsorption efficiency. And our results showed that this material was more efficient due to the amine group that is on the surface. And the cross-linking reduced the surface area, whereas our maximum adsorption about 69.9 at 100 milligram per gram, 100 milligram of adsorbent and 25 degrees. And the absorption capacity followed pseudo second order kinetics indicating chemisorption. Now we are done with aqueous phase adsorption and we are going to open a little bit about energy storage systems. Like I introduced, carbon electrodes in supercapacitor electrochemical hydrogen storage is versatilely used. In fact, it is sustainable, and even in lithium batteries, they still use some graphites or even some engineered nanotubes. So the characteristics of carbon is exploited, and this characteristics is the high surface area and the porosity. And to know the relationship between the capacitance for supercapacitors or even storage for hydrogen storage and the surface area, we have this model where CS is the specific capacitance per unit surface area, and C is the specific, and A is the specific surface area. This means that indeed the capacitance will increase proportionally with the surface area as long as the pores are accessible to the ions. Okay? So another very fascinating material that we used is wasp hive. Pardon. Wasp hive is a material that is very fascinating indeed. Here in UNAM and in Mexico as a whole, wasp, which looks like a bee, but it is not a bee, is a major challenge for bees. They invade bees colony, they kill them, and you guys know, of course, what bees are and the interesting aspect of bees. So there are a lot of money going into removal of wasps and the hives and so on, destroying their colonies so that the bees can thrive. Hence, we use wasp hive to produce activated carbon. A student here in Mexico produced this material, and this material is very fascinating because the wasp, which of course looks like that, the honeycomb of the bee, the micrograph of this material also have interconnected pores in it. And our isotherm, of course, is a combined isotherm, purely of 2 and 4. So the material contains about 69% carbon and 17% oxygen with some inorganic elements. And the isotherm is a combination of type 1 at small pressure and then type 4 at medium to high pressure. The PET surface area here is not very large, it's about 765 square meter per gram, but the pore size is within reach. Our Raman spectroscopy that we looked at shows a typical D band and G band. And the deconvolution, we found out that it has 1.6. The ratio between the D and G band is 1.62, which confirms that that material we produce, which is the carbon, is amorphous. And of course, it will be amorphous because it was produced at about 800 degrees Celsius. Electrochemical characterization of this material shows that we have an excellent capacitance, and we tested it in different electrolytes. And we found that the best electrolyte for this was acid electrolyte. Of course, people will ask, why not use neutral electrolyte compared to acid electrolyte? And I'm going to tell you the reason a little bit now. One of the very fascinating things that we found in this study is that the DOE requires that the discharging time of that supercapacitor or even hydrogen will be in short minutes. So here we could achieve very short time of discharge in this range, in seconds, for that matter. So the contribution of the electrical double layer we found from our study is quite huge compared to the Faraday processes. And this material could be used in terms of its charge retention and capacity retention for over 5,000 times of charge discharge. You could see the retention capacity only decayed a little bit to up to 80, and the columnic efficiency of our material is 100 and was stable throughout. So this shows that this material is very fascinating in itself because we were able to have up to 225 farads per gram, which is actually one of the best performing materials, among the best performing material for carbon electrode. Of course, if you use metals and the rest, you may have a far higher capacitance, but then you are synthesizing those materials to be used. Also, we found that we cannot use neutral electrolyte because it gives low capacitance. And since the surface of our material is also electrically neutral, so the neutral electrolyte do not work in this. So acidic electrolyte forms a strong double layer and increases the capacitance that we have. Another fascinating material that we use is the super adsorbent of disposable baby diaper. And I'm going to make a little joke. When I came to Mexico, I had a little baby, and then I never knew that the cost of diapers are very, very, very serious. And babies use diaper every 2 minutes. So after having a lot of diaper, like massive tons of it, I started thinking of how to dispose them. And then I thought to myself, we can also use diaper to make carbon. And then I selected the ones that they urinated on. And then I tried to remove the adsorbents from the urine itself, dry it, and simply use it for hydrogen storage. That work was actually conducted by my master's student who currently is doing PhD in Thailand. And the idea is that we are trying to store hydrogen electrochemically. So hydrogen storage, electrochemical hydrogen storage is stored as an atomic hydrogen on the surface of the carbon, not free ions. So there are two mechanisms of storage. We have adsorption of hydrogen on the surface of electrode, where hydrogen is stored in atomic form. And then we have insertion of these atoms into the bulk of the structure of the electroactive material, sometimes forming metal hydrides or chemical bonding. So we tested this material for hydrogen storage, and we found this is the micrograph of just the diaper, and this is the micrograph after we have produced activated carbon. We obtained a significantly high surface area material of 2,555, and we were able to store 6.604. The previous DOE, that is Department of Energy United States capacity, is about 5.5, although it is now reviewed to about 8 or 9 weight percent. But we were able to exceed those previous standard to have 6.604 weight percent of hydrogen stored in our material. The worst sample here, of course, stored far more little than that. And the discharge time set according to the DOE is between 3 to 5 minutes. But you see, we saw that we could also achieve these 3 to 5 minutes in current densities of 1 and 2. So when we test all the surface area or the surface that are confined, we found that the surface confined processes shows that the contribution is the entire of the experimentally obtained currents. And then we knew that we are on the right track. Now this study is being expanded to understanding clearly how these hydrogen atoms interact electrochemically with the surface of our activated carbon, especially when we add something heteroatoms like nitrogen in it or quinone and so on and so forth. So this is the result of the entire work. And now we come to the final case study, which is the glycerol valorization. Glycerol, because we are in green energy, our group here is the umbrella group is bioenergy. Our group here works on biodiesel production. 10% of 100 of about 100% biodiesel produced is glycerol. These glycerol are low quality. They have a lot of water. They have some other chemical components that then they are discharged completely. So during my time, I started thinking, how do we use glycerol? We know of several pathways to valorize glycerol, but also we can produce glycerol either by combustion or by obtaining a material which has superior characteristics. This material that we obtain is biochar from glycerol, and we used it to valorize glycerol or to convert glycerol into fine chemicals of monoacetanes and diacetane. So, how did we do that to produce carbon from glycerol? Simply, we added a concentrated sulfuric acid, which acts as a dehydrating agent and partially carbonizing this material. Eventually, we had carbon full of sulfonic groups. These sulfonic groups can tailor the esterification reaction of glycerol with acetic acid to produce triacetanes or diacetanes. One of the uses of this diacetane and triacetane in biodiesel is that they are fuel additives. So usually we produce this, and I always call it glycerol bread. So, but it's not edible. You cannot eat this. We produced, and this is how it is. This material is dense. It really do not have surface area, and it has very irregular morphology. However, it is rich in sulfonic groups, which is necessary to catalyze our reaction. When we try to produce this material, we also could find that we have carbon-rich material. And after using this material for 7 times, this material did not degrade or deactivate. In fact, we had continued production for over 10 times of recycle without any problem. So we tried to characterize to understand this material. So we looked at the SPS of the material, that is X-ray photoelectron spectroscopy of the material. We found some of the elements that are there of sulfur, carbon, and also some sulfonic groups, of course, due to the sulfur. We have the carbon-carbon chain and the carboxylic groups. These groups are very essential in propagating our reaction, and eventually we had very good reaction. So our material was able to produce up to 87% of combined diacetylglycerol and triacetylglycerol as we have it. And H2SO4 acts as both dehydrating and sulfonating agent, reducing volatile release and tar formation. Eventually, the sulfonic groups and carboxylic groups, which have high Bronsted acidity, helped us to obtain rich fill additives as you see it here. And this is our material reusability up to 7 times without any decay, without any difference. And this is one of the promising works that we have done so far with carbon material. So, what is the contribution, impact, and innovation in my research? The contributions are we have developed strategies to produce porous carbon from diverse biomasses and demonstrated its application in several energy fields. Also, we have produced material from liquid glycerol and evaluated carbon for energy storage. So we had several impacts, including advances in sustainable waste to carbon valorization strategies, provide scalable solution for water purification, renewable energy, and green catalysis, and strengthen circular bioeconomy by converting waste into functional carbon materials. So we have actually key innovations, novel biomass sources, like nobody has ever thought about diapers or wasp hive to high surface area carbon. We have also integrated processes of adsorption, catalysis, energy storage with a single carbon platform. And we have actually had fast adsorption kinetics and multifunctional functionalities. So the pathways for next research and my concluding remarks is to have a scale-up for synthesis method for industrial feasibility, have detailed optimization and functionalization for selective adsorption and catalytic activity, explore hybrid material, for instance, carbon metal, carbon polymer, composites, and long-term performance studies, regeneration of this material, and life cycle assessment. So, my closing remark, porous carbon material derived from biomass and waste exhibit excellent versatility across both environmental catalysis and energy storage. So future research should bridge laboratory innovation with real-world implementation for maximum impact. So this is my group. These are my students that worked previously with me. He is now in Thailand. He is with me in PhD, and now he is doing his master. Sorry, she's doing her master's, and the both two are submitting their master's thesis. Thank you very much, and I am attentive to your questions.
Thank you very much, Patrick, for this wonderful and very interesting presentation. I would like to ask you one very technical question. In the storage use of the activated carbon, some of your graph present hysteresis, but others not. Do you can explain why are there different behaviors?
Yes, I will tell you that. The carbon that we produce has different porosity. So these differences in porosity because the hysteresis, okay, we talk about the hysteresis. It is that space between adsorption and desorption isotope. Why we have that hysteresis is because of the differences in the porosity of that material. And we have differences in pore distribution. So the material has some with more micropore than mesopore. So the hysteresis, of course, is capillary condensation that we see happening in the pores of this material. So if you have micropores that is far more nano than that of the molecular imprint of nitrogen that we are adsorbing to show the surface area, maybe you won't have hysteresis in that platform. But then if you have some mesopore or some micropore and this nitrogen, condenses in the pores of your material, and then by differences in pressure, because it's relative pressure, it tries to dissolve and it takes a longer time to be removed. Then you have some hysteresis. So this is exactly why some carbon are different from the other. It all depends on one, your activation conditions that you have, the porosity in your material. It's very necessary. Thank you very much.
Thank you, Patrick. And I am sure that you are going really in producing in a sustainable way this activated carbon, porous carbon. But how we can measure how close we are of really produce sustainable activate porous carbon?
Well, the the idea or this question, the answer lies in conducting of life cycle analysis from cradle to cradle or cradle to grave. So if we could employ the tools of techno-economic analysis, life cycle analysis, exego-environmental or exeg analysis, we were able to see not just about the sustainability, the cost, we will see sensitivity analysis of some factors that may influence material, and we also be able to see holistically the nature of producing activated carbon. And I would want to tell you here that activated carbon production is not very cheap. Although we obtain this biomass purely from resources that are waste, but then if we try to evaluate the energy that we impute in the system, hence, and then evaluate some of the equipment cost, labor cost, and so on and so forth, you could see obviously that it is not that very, very cheap, especially when you have to employ chemical activation. Because if we do physical activation, we could get CO2 gas and then use it to make the activation. In that way, it reduces the cost compared to the chemical activation. So this is what I want to say. Thank you very much.
Oh no, Patrick, really, really, I like the way that you tackle the problem to avoid the problem using waste and different ways in different matters. Really, I love the way that you are doing these kind of things. And well, Patrick, I think that we need to close. We have no more questions
Oh,
in this moment,
okay.
but
Okay.
it
Thank you.
was a wonderful talk, and I just invite the people that is listen, then you can share the link in
Yes.
our YouTube platform
Yes.
to see another time or to share with some friends this
Yes.
wonderful presentation.
Thank you very
Do
much
you
for having
do
me.
you want to add in another thing?
Yes, I just want to acknowledge Dirección General de Asuntos del Personal
Mm.
Académico de DEGAPA for funding majority of our research, and some of my students, Estefania Duque Brito, Giovanni Mondragon in Thailand, Luvia Morias Santos in Instituto Politécnico Nacional, Diego Rabato in Zaragoza, and my very profound collaborator in the United States of America, Judo Collier, and all my students for contributing, for working together and interacting. And most especially, I want to say that our group is accepting students from all walks of life, and you can come and join us. Working here, especially in Mexico. Mexico is a very great country, one of the best countries that I have ever lived in, with very good places to go to, very nice people around, good food, tacos, and so on and so forth. And you can come to us, you join us wherever you are. We can help you with some of the processes, and we can also share with you some of the processes for making it easy for you to come and join us here in Instituto de Energía Renovables de la UNAM. Thank you very much again, Dr. Deorio. I really appreciate the time.
Patrick, sorry, I think that a question comes from an students
Oh,
and,
okay.
and say, what do you consider the most promising real world application of porous carbons in the short terms? Environmental remediation, energy storage, or catalysis? I am sure this question is because one student want to go to this wonderful application that you present.
Of course, environmental remediation is, of course, the very immediate and in fact, currently used because you have carbon filters. They call carbon filters. It is packed with activated carbon, so used for removal of several pollutants. It is practically used in several wastewater treatment plants worldwide for removing of recalcitrant materials, including dyes, especially dyes that are in color. And several industries use that. In terms of supercapacitors, of course, it has very promising use. However, we are looking for a way because the capacitance is directly related to the surface area of the material. We are looking for a way to have to reach at least 4,000 square meter per gram. If we can reach 4,000 square meter per gram, maintain microporosity, and maybe have some functional groups of nitrogen, it is very possible to have almost the same performance with metals or synthesized metals that is currently being used for supercapacitors. And of course, if we could do this, it is very possible. And to do this, there is a way out, actually. We are actually doing that. That way out is that we are going to shift our focus from the conventional activating agent to an activating agent that can be able to create pores, rich pores, that can be able to completely open the matrix of the carbon. And to also do that, we are looking for a way not just to thrive in physical activation or chemical activation, but to see a way to combine both physical and chemical activation. And in so doing, what we are doing is we carbonize, and instead of doing physical activation with CO2 or steam, we are going to employ a new material, chemical material, to activate it. So it has become one step of the physical and then one step of the chemical method. And by so doing, we should be able to have at least close to 3,700 up to 4,000 degrees. But then we must know that we should look for the right material. If you have biomass resources that is rich in lignin, then definitely it is rich in carbon. Hence, you will have far more higher surface area with this material. So this is my answer to the question.
Perfect. Thank you very much, Patrick. And I appreciate you having you here and for really this very inspiring presentation. Your work highlights the versatility of porous carbon in addressing urgent challenge in energy, environment, and catalysis. And we invite you to stay connected with the Center for Mexican Studies UNAM UK and to join us in our upcoming seminars. Thank you again for
Thank you.
all your participation, and we look forward to see you in the next session. Thank you very much.
Thank you very much, and do have a nice day. And thank you everybody for listening. I really appreciate it. Bye.